Well. Let's see, are we live now? I thought I'd get on a little bit early today so that we could do the sound checks and the video checks real quick. If you could give me a little note in the chat there and let me know if we're coming through okay and the volume is good enough, then I'm going to just do a couple of focus checks and we'll get going. While we do that, I think I'm going to go ahead and bring up the page for the video to make sure it's going out okay. Yep, looks like everything's going all right. Volume is fine. Let's do a quick focus check here. Make sure that you guys can see the slide rules okay. And then we'll get started. Everything in decent focus for you? The focus all right? It looks pretty good to me. Hey, Beta. I've got my favorite Castel as well. Okay, Judy says the focus all looks good. So let's go ahead and get started. Well, I'm Bob the Science Guy. I have a YouTube channel, a couple of them actually. And one of the things that I like to deal with is something that is called STEM education, science, technology, engineering, and math. Well, nothing defined a mid-20th century American engineer as much as their slide rule, a pocket protector, pair of horn-rimmed glasses, a white shirt, and a skinny tie, and a buzz cut. That's my father. I didn't go into engineering myself, but I've always had a love for slide rules because I always thought that they were a fascinating way of looking at mathematics because you had a familiarity with numbers that you just don't get with an iPhone or a calculator or something. So I've done a series of tutorials on how to use a slide rule. And I go over all the different scales and the different types of slide rulers, etc. But I thought that I would do one overall video for people that are out there that are unfamiliar with slide rules to try and figure out what slide rule they might want to purchase, either to learn how to use one or to use for work. You can use it in a variety of things, be it figuring out how many cinder blocks you need for a wall or building a bridge. The last aircraft, major aircraft that was built using slide rule technology was the SR-71. During the 60s, we went into computers, and in about 1973, the electronic calculator came out at a price that people could actually afford. I remember my mother getting her first 4-function calculator, which only ran her $300 in about 1972. By 1975, everybody had an HP, and the slide rules kind of went out of style, and they stopped making them about 1975. There's only one company that I'm aware of right now that still makes quality slide rules. So let's just kind of pop over here to the desk and have a look at a couple of slide rules. Now, I've got this broken down into a couple of different sections. These are basic or student level slide rules, and we're going to start off with this guy right down here to kind of just introduce the concept somewhat. Yeah, that's coming through. Now, this is a slide rule. And the characteristics of a slide rule are this. We have a body of the slide rule, and then we have the slide, and then we have the cursor with a hairline on it. The body of the slide rule is also sometimes called the stator. Now, this particular slide rule is designed for a specialty task. This is a conversion slide rule. It's not a slide rule like you would consider, but if you want to be able to confirm to convert meters to yards or meters to feet, square meters to square yards, etc., you can use a device like this. And the way that you would do that is simply line up your appropriate mark with the number on the slide with the amount on the stator. So for example, if we want to figure out how many feet are in 5 meters, we put the meter mark right underneath the 5, and then we read out here to the foot mark, and we come up to a little bit over 16 feet. Now, starting with that principle, we'll go on to an actual slide rule, and that's what these are. Now, a slide rule, again, has got a body called the stator. It has the slide, it has a cursor, and it has the hairline. You can see that's the common feature on all of these. Now, the way a slide rule is set up is these scales are what they call logarithmic scales. And when you take the log of two numbers and add them together, that is the exact same effect as multiplying those numbers. So for example, if we wanted to multiply 2 by 3, we would put the index line, which is the 1 on the slide, over the 2 on the stator. And then we'd simply read out to the 3 and get our answer, which of course is 6. Now to do division, what we do is we take the number that we're doing something to, in this case 6, and put it on the stator or the body of the slide rule. And then the number that we're operating on it with, say 4, we'll put that on the slide. So what this would do would divide 6 by 4, and then we would read our answer down here at the 1. And there we go, 1.5. Now, that was my grandfather's slide rule. He was a civil engineer, graduated from Cornell in 1929, and then went on to head the Army Corps of Engineering Department of Hydrology in the Great Lakes. He was heavily involved in the Niagara River projects around the power stations and in the St. Lawrence Seaway. And when he retired in 1962, the year I was born, he attended the opening, or should I say reopening, the St. Lawrence Seaway, and basically had dinner with the Queen. Now, let's start off with this one right here. This is a very basic or student level slide rule. It's made by Sterling, and you can get one of these on eBay for less than $20. Now, there are a number of scales on the slide rule. The main scale is going to be the C and the D scale, and that's the one that we just used to multiply 2 by 3 and divide 6 by 4. Now, the operation of that, we've kind of gone over real briefly, and I've got tutorials for that. But we have another set of scales on here, and these are the AB scales. The AB scales are half the length of the CD scales. And as a result, the relationship between these two scales is if you have a number here, or excuse me, if you have a number here, its square root will appear down on the CD scale. So if you put the number on the AB scale, the square root will appear down on the CD scale. And I'll show you an example of that because there's a couple little tricks. So let's, for example, you don't even need to really use the slide for this because you can use the A scale and the D scale. But if we were to look at 9 on the A scale, we would look down to the C scale and the D scale and see its square root, which is 3. Now, there's an interesting trick that you have to remember with the AB scales, and that is that if it's an even number of digits to the left of the decimal place, you read it on the right, or excuse me, on the left side of the AB scale. If it's, I'm sorry, I may have said that wrong. If it's an odd number of digits to the left of the decimal place, you will read that on the left side. If it's an even number, you'll read it on the right. So, for example, we just saw 9. That's a single digit number, and that's odd. Well, what about 16? 16 would be 1, 5, 6, and then we read down and there's a 4 right there. That's the square root. Now, what about 225? So let's go down here. There's the 2, there's 20 and 25, and if we read straight down, we find the answer is 1.5, which brings up another point. We have to figure out where to put the decimal place in here, and I've got a couple of tutorials, you know, as I go through the different scales on the slide rule, that'll show you some aids in doing that. But the square root of 125 would be 15. So that's the basics of a student level or basic slide rule. Now there's one more scale on here that's kind of an interesting scale, and that's called the CI scale. And that is simply the inverse of the C scale. So for example, if you want to multiply 4 by 6, it's rather inconvenient to do that because here the 6 is way off to the side. Now sometimes one way that you can do that is you can bring the other index over and come up and find the 6 here. And then read down and you'll find the answer is 2, 2, 5, 2, 4, 24. Now with the CI scale, you can actually kind of go backwards. Say you wanted to multiply say you wanted to multiply 4 by 2. Let's go see if we can do this right. Where's that CI scale? And we've got 8. All right. So the last scale that I want to show you on this is the K scale. And that's down here at the bottom on this one. The K scale, like the AB scale, was squares and roots. The K scale is cubes and roots. And we have some other special rules to remember with that, but let's show you the first one here. So if we put 8 on the K scale, we read right up to the D scale and see its cube root, which is 2. Now, we had 2 complete scales up here on the AB scale. We have 3 complete CD scales down on the K scale because we're dealing with cubes. Now, which scale do we use? Well, as you recall, up top, we used odd on the left and even on the right for numbers past or to the left of the decimal place. Down below on the K scale, we have ones, we have tens, we have 100s. Then we go back 1,000, 10,000, 100,000, a million, 10 million, 100 million, 1, 10, 100. So depending on what the number is, we just did 8. That's in the ones. Well, let's think of one that has 2 digits on it. How about 27? 27 would be right there, and we read up to the cube root, and that is 3. All right. What would the cube root of 200 be? Well, what you would do is you would bring it up here. 200 is 3 digits past 200 is 3 digits past, excuse me. 200 is 3 digits past to the left of the decimal place. So the answer would be 5, 5, 5, 6, 7, 8. About 5.8 and a half cubed would give you about 200. And you can check that on your calculator if you wish. Well, that's what I wanted to cover on that. Now there's one more function on these basic slide rules that's kind of important as well. And the way you get to it is you just simply take the slide out and reverse it. And on the back side of it, you'll see these 3 scales here. This is the S scale, and the t-scale. That's sine, cosine, and that's tangent. The L scale on this is for the mantissa of the logarithm. I'll tell you what, go ahead and go over the logarithm tutorial that I have coming out next week, and that'll tell you how to use that very well. But here's an interesting thing that you can do with the Here's an interesting thing that you can do with the sine and the tangent scale. Let's take a standard right triangle. Let's go 3, 4, 5. That's a pretty standard right triangle. Now let's look at the trigonometric values of that triangle, and we'll look at this angle right here. Now the sine of that angle will be 3 over 5, or 0.6. The cosine of that angle will be 4 over 5, or 0.8. And the tangent would be 3 over 4. Now, the question is what's that angle right there? Sometimes that's a little difficult because you have to use functions called the arcsine, the arccosine, and the arctangent. But actually, it's a lot easier when you use a slide rule, and I'll show you exactly how to do it. Let's take the sine of this angle right here, which is 0.6. So we'll put that on 6. And then what we'll do is we'll actually read up, that is the sine of some angle. Wait a minute, am I doing that right? Hang on half a second. Give me a moment, I think I'm actually doing something wrong here. Sine, yeah, that should be. I'm obviously making a mistake here. This is the fun thing of doing this live. I'm having a brain cramp of some sort. Well, let's make it a little bit easier real quick. Let's look at the tangent real fast because I'm obviously doing something wrong here and it's taking me a moment to figure it out. The tangent is going to be 3 over 4, 0.75. So we go to 0.75 right here, and then we read directly up, and we can read off the angle of that angle on the tangent scale. So we've got 35, 36, just shy of 37 degrees. And that's the way that works. I wonder why that didn't give me the correct answer on the sine. I'm obviously doing something wrong here. Well, I'm obviously screwing something up. We'll figure that out in a minute. Let's go ahead and go back here. Okay, so let's take that off of the desk for a minute, refocus our eyes, and see if there are any questions that we have. Let me check out let me have a look at the chat here and see if we've got questions so far. You guys are talking amongst yourself, it looks like. Yeah, I know the arc sine is about 36. Beta, that's correct, but for some reason I wasn't seeing it on my slide rule. I obviously had something that I made a mistake on. I'll have to have a look at that. That'll be one of my little things that I'm going to follow up on when I get out. Now, those are basic slide rules, and those would be pretty typical of students that were in high school or their first year of college going into non-technical fields. And, you know, this is something, you know, that Masons would use, or people that just needed something in their desk to do math real quick. Now, there were people that actually used slide rules for a living, and they had a little bit more complex slide rules that had additional scales on them. And those are the ones that I'm going to go over right now, along with my recommendation of the slide rule that you should get if you really want to learn how to use a slide rule, and you can get it for about 40 bucks. So let's go ahead and have a look here. All right, I think everybody can see this okay. There it is. I'm actually going to zoom this out just a little bit so you can see it a little bit clearer. Just going to double check the focus real quick. The video camera is on a flexible stand, so when it moves even a little bit, it tends to bounce for a minute, or if I accidentally bump the desk, it'll bounce. All right, so here's a typical slide rule that we just used. This is my grandfather's slide rule, and underneath it is my father's slide rule. My grandfather was a civil engineer. My father was a mechanical engineer. We used to always joke that Dad designed weapons and Grandpa designed targets. Now, my father's slide rule is what's called a KE slide rule. That's the manufacturer that made it. And it's an American slide rule, and unfortunately, I don't really care for them as much because they're kind of bland and unimaginative, but they do the job. Neil Armstrong used a KE slide rule. Now, you'll see right here we have the D scale. We don't have a C scale on this because it's on the other side of the slide. And this has got a reversible slide as well. And it's got an A and a B scale. There's the K scale, the L scale. And then here are some of the inverted scales. You can invert the C scale, you can invert the D scale, you can even invert some of these other ones, the A and the B. Now, you'll also see something called an LL scale on it. Those are log-log scales. We'll go over those in a minute. Now, this is what's called a Deplex slide rule, which means that if you flip it over, there's a whole nother slide rule on the other side. Here are more of those log-log scales. There's your C and the D scale. Now up here you have something interesting. You have a CF and a DF scale. Now, a few minutes ago we did something where we multiplied 4 by 6, and we ran into a problem because if we bring the index out here to 4 and try and read the 6, it's way the heck out here. Well, what would happen if instead we cut this scale off right here at pi, 3.14, and then we took this half of the scale and we moved it over to here? Well, that's what we do with the CF and the DF scale. These are what's called folded scales. And the reason that they're folded is that sometimes it's more convenient to use to multiply something from here up to a folded scale and then read it off at the index on the folded scale than it is to try and just use the straight CD scale. I'll have an actual tutorial on how to use some of these special scales. Now, the other scale that you'll see on here is the LL scales. Now, the LL scales are used for logarithmic calculations. A good example of that would be carbon-14 dating. So to carbon-14 date something, for example, the half-life of carbon-14 is 5,730 years. So we go here to 5,700, that's 750. So we're going to go just a hair back. And because it's the half-life, we're going to... No, did that wrong order. Order is very important in slide rules. The half-life is put up on the LL scale. And here you see it's 0.5. So that would be a half-life. And then you put the actual value of the half-life underneath it. So we've got 5,730 years. Well, say you have an artifact that has a little carbon in it, like a piece of charcoal from a fire in a cave somewhere. Well, when did that charcoal, how old is that charcoal? When a tree is growing, here, let me switch over to the other one. The basic principle behind carbon-14 dating is that as a tree is growing, it's exchanging carbon with its environment. And there's a certain amount of carbon-14 in the air. And as a result, a certain amount of carbon-14 gets incorporated into the wood of the tree. When the tree dies, it's no longer exchanging that carbon, and the radioactive carbon-14 begins to deteriorate. So say we have a piece of charcoal from a fire in a cave, and we find that it has 1.5% of the original carbon-14 that would have been in place when the tree was alive. How old is that artifact? So let's go back down here and do it. Now I've got a whole video on this, so don't feel the need to actually memorize how this all works. So we've got 0.5, that's the half-life, and then we bring it down to 5.73, and we put that on the movable C scale. Now what we need to do is we need to go down here to 1.5. And that's 1.5%. That would be 0.015. And notice the scale goes backwards. And also notice that it's in red. And then we simply read down and we get our value. Now our value in this case is going to be 34,700 years roughly. And that's how old that piece of charcoal would be. That's what these LL scales are used for. Now, that's a KE scale, or a KE slide rule. This is a Faber-Castell slide rule. This is a German slide rule as opposed to an American one. You see there's a little bit more in the line of color on it. And the scales are arranged a little bit differently, but they're essentially the same scales. We don't have anything special here. Normally on one of the student slide rules, if you look at the tangent function, which would be these t numbers, the angles would go in one direction, and then you'd have to read in red back in the other direction to get the tangent. Here we have it split up into two. We again have the folded scales. We have an inverted scale. We've got the sine scale. Then we have something down here called the ST scale. The ST scale uses something called the small angle approximation. When you get below about 5.7 degrees, if you were to calculate that angle in radians, that would be approximately equal to the sine of that angle and the tangent of that angle. It's a small angle approximation. That's very useful when doing parallax calculations with a transit of Venus or doing stellar parallax to try and figure out how far it is to the sun. So that's what that scale's for. And on the other side, we just have our standard scales here. Now, this is kind of an important slide rule that I'd like to go over with you. It's got a couple of really nice features. This is an engineering level slide rule. It's a Pickett is the name of the brand. And this slide rule is an N3 and it's from 1962. Now, we have all of our standard scales here. We've got the CD scale, we've got the AB scale, we've got the K scale, we've got our trigonometric function scales here, the small angle ST scale, the sine, cosine scale. Sine is in black. The corresponding cosine is 90 minus the sine, and you see that's in red. So you can actually, the sine of 10 degrees, for example, is the same thing as the cosine. of 80 degrees. But we do have a couple of interesting features on this, and that's these scales up here on top and down here on the bottom. Notice there are two what looks like square scales on the top, and there are three that have the root brackets that have a little 3 on it on the bottom. One of the things that you can do with a slide rule, and we do with the LL scales, is we take one long scale, and then what we do is we divide it up into manageable pieces. That's what this is. The scales here on top that are square root scales are twice the size and cut in half of the AB scales. So, for example, if we wanted to look at 4, all right, what's the square root of 4? We would come over here to 4, or excuse me, the square of 4. We would come over here, 4 would be the square root of 16. There's 1, 1.1, 2, 3, 4, 5, 6. So 4 is the square root of 15. What is 15? Well, 15 would be right here. 15 would be the square root of 125, it looks. So you see, it's just a little bit more precision. That's what you have here. And you can do the same thing with cubes. So rather than try and memorize where you're looking, which half of the scale you're looking at, all you have to do is just dial in the number. So for example, here's 2, 2.2, 27. Let's see if we've got that right. We want to go up here to 2. Should be right in this general area here. Okay, come on, guys. Well, in any event, there's 8. What do we got here? Boy, the slide rule gods are not with me today. I'm either making really stupid mistakes here, or I probably should have just refreshed myself on these a little bit earlier. See, there's 8 right there. We should be able to read up and get the 2. And I don't see the doggone thing. So obviously I'm making a mistake somewhere here. But in any event, that's what those are for. On the other end, you're going to have all the folded scales, and you're going to have the LL scales. Now, boy, that's embarrassing. I actually know how to do these things. I must just be having a brain fart or a boomer moment today. But the reason that I wanted to bring up the Pickett N3 slide rule is that you can use this online. There's a virtual version of this, and I'll show that to you here in a couple of minutes. And the other thing is that this is about a $40 slide rule that has everything on it that a slide rule should be expected to do. There's only one scale on this slide rule that is missing, in my opinion, and that is a P scale, or a Pythagorean scale, and we'll go over that in the next section. But if you wanted to buy one slide rule to learn everything that you needed to know about the slide rules, get yourself a Pickett N3. So let's check the chat real quick. Yeah, I'm sorry I'm having brain cramps today. This is one of the things with slide rules. You definitely have got to have a really good familiarity with the relationships. And apparently I'm just having a moment today. All right, so I think that's something that I'm going to have to fix when I do the production version of this video, or at least do the editing. Now, we've got a couple of other slide rules that I'm going to go over right now. And, that Pickett or one of the KEs would be very good for your standard professional person like an engineer or an architect, or somebody that really wanted to learn about slide rules. If you want to go absolutely insanely crazy, and you've got $250, $300 burning a hole through your pocket, you can buy what is generally considered the very best slide rule ever made. And that is the Faber-Castell 2/83. Let's go ahead and have a look at a couple of these. This is considered one of the best made and most accurate and beautiful slide rules ever made. This came from 1975, right at the very end of the slide rule era. So you see it's got a nice white background. It's got some colors on it to help you keep yourself straight. It's got a very nice slide. Notice that there are some marks on the slide. What these marks are is if you happen to put, for example, the diameter of a circle under the mark. So say you had the diameter of a circle, you could actually put that under the diameter mark, and then you could actually get the area of the circle from it. And we can do that on both sides. So if we had a circle that had a diameter of 2, what would the area of that circle be? 3.14. And that's what that, and you can do that. You can also transfer kilowatts to horsepower and things like that. But there's a couple of interesting scales on this slide rule, and I'm going to point them out. Now you may recall that we talked about the sine scale on the slide rule. So this would be the sine of 10, and it would be the cosine of 80 degrees. Now, with a slide rule such as this, what you can do is you can get the sine of 10 degrees and read it off of the CD. Okay? But then what you can do is you can come right down to the Pythagorean scale, and you can also read off the cosine of that same angle, 10 degrees, without having to go to the other side of the slide rule. So the P scale is a very important scale to have on a slide rule if you're doing any sort of trigonometric functions. It's just a really nice to have thing. The Faber-Castell also has 2 additional scales that you don't see on other scales, and that is these W scales. Now recall that when we talked about the AB scale here, we said that the AB scale was half the length of the CD scale, and as a result dealt with squares and roots. It was the relationship between squares and roots. The W scale is twice the length of the CD scale, and it's so long, on a 10-inch slide rule, it's actually split into 2 pieces. You've got W1 and W2, and there's W1 and W1 prime, W2 and W2 prime. The reason that you use these, the purpose of the W scale is to allow you to get greater accuracy in multiplication and division. Slide rules, their accuracy in significant digits is dependent on the length of the slide rule. The standard slide rule is 10 inches. Now, for convenience, that's an engineering slide rule as well, and it's 5 inches long. This is called a pocket slide rule. And it's good for quick calculations, but it's only accurate to about 2 significant digits, maybe 3 on a good day. A standard 10-inch slide rule is accurate to 3 significant digits and maybe 4 on a really good day. If you have a longer slide rule, such as this one, this is an Aristo Studio 20-inch slide rule. This is good to 3 to 4 inches all day long. And the reason being is the length of the scale and the distance between the numbers. The scales are exactly the same on both these slide rules. However, being this is twice as long, you got a lot more precision when you look at the hairline on it. Now, if you need stupid accuracy, you can get a slide rule that is 500 inches long. And that is good to 5 significant digits. And that's called a Fuller calculator. Now the Fuller calculator, this is the scale on the slide rule here. It starts up here at 1, it wraps around this cylinder, all the way down to 1 again here, just like the beginning and the ending of the CD scale. And simply by placing your index lines where they need to be, you can actually get 5 significant digits out of this. This used to be used, I saw this in my training when I started college in the chemistry lab. They had one of these there, and that was in 1980. This particular model was built in 1952. Yes, that's a little bit more expensive than the 283. But again, if you want to get into this, you want to probably get a good all-around slide rule that's reasonably cost, that's got a reasonable cost to it. Get that Pickett N3. So let's put those down. Let's go over a couple of specialty slide rules. Now, in aviation, we have something called an E6b Flight Computer. And with the E6b Flight Computer, we can calculate fuel, speeds, distance remaining on available fuel. It has a slide rule on it as well as CD scale, so we can do basic calculations. We can do pressure, altitudes, etc. This is an entire video to learn how to use that. Here's another example of an aviation slide rule. This is a landing distance calculator. So what you do is you basically take into account the normal landing roll of your aircraft on a paved runway. And you put into this other factors. Is there a density or pressure altitude that's abnormal? Is the runway wet? Is it sod rather than concrete? You can do all of these things here. You can find your takeoff distance and, more importantly, your landing distance. Takeoffs are optional, landings are mandatory. And if you're coming into a runway in northern Michigan that's got some ice on it, and it's abnormally warm that day, say we get a little hot spurt and it's 50 degrees out, we can actually figure out whether or not we're capable of landing on a particular runway if the runway is long enough. And it'll also take into account, for example, we have to touch down at landing speed at a certain distance down the runway, or we have to go around. Well, if that distance goes by, we know that we're not going to be able to stop in time to stop at the end of the runway. Now, there's one more that I wanted to go over with you, and let's see where that is. Just had it. Oh, there it is. Let's go ahead and get off the desktop because we're not going to use this one here too much. Now, as you can tell, this thing's green. What's that mean to you? This is from 1946. It's not a true slide rule because there's no slide on it, but there is this plate that has a variety of graduations on it, and it's got a movable slide to try and figure out, well, given this, it gives you the relationship between a couple of numbers. This is an M23 graphical firing table. Now, this is used to determine the elevation of the tube when you are firing a 105 millimeter howitzer or 155 millimeter howitzer based on the type of projectile and the number of powder bags that you're using. Now, this will take into account the factors that you need to use for curvature of the Earth, for Coriolis, and it'll tell you exactly where you have to name that tube or aim that tube in order to have a chance of getting in the same postal zone as the target that you're trying to hit. Now, this is used for the ranging shots. So is it long, is it short, is it left, is it right? You've got some second lieutenant and a guy with a radio sitting in the woods near your target, and he's calling in corrections on your artillery fire. That's to get the first shot, and then you walk it into the target and do the fine tuning under direct observation over the horizon. Well, I hope that that was at least a nice introduction to the slide rule and some of the different types of slide rules. Like I said, this is what you want right here, is a picket N3. Now I'm going to put, as a matter of fact, it may already be in there. Let's see. Yeah, there are two links that are important in the description of this video. The first one is a link to the International Slide Rule Museum, and they have discussions of every slide rule known to man there. They'll tell you what scales are on it, they'll tell you, tidbits of information about it, etc. But more importantly, they have what's called virtual slide rules there. So let me see whether or not I can go ahead and bring that up. Now that's looking pretty good. So we're going to come down here and we're going to go to the virtual slide rule right here. Derek's virtual slide rule gallery. Now, for example, here's a pretty basic slide rule. As you see, simply by moving your cursor, you can drag that cursor around. You can move the slide, and then you can actually move the whole thing around. So here's one of the basic slide rules. Let's look at the scales that are on it. We've got our CD scale. We've got our AB scale. We have a K scale. We have our trig scales, and we have a logarithm scale. Now, you can also flip it over, and this is very similar to what we had on that first slide rule, which is pretty much a dedicated slide rule just to do these conversions. Now, if you go back, here's the picket N3, and that's the one that I use. Notice it doesn't have that, what they call eye saver yellow. This is a more traditional cream colored slide rule, but it works the same way. And you can bring it back and forth. It doesn't have a fuller on it, but you can flip it over and here are all your scales that you can use. You can play with this a little bit and decide if it's something that you would be interested in getting a hold of. So really, that's all I had for you today. I've got a little bit more work to do on this. I'm going to see if I can fix my screw-ups there real quick and find out where I went wrong. But other than that, there we go. Now, right now, we're going to be over in the Discord server. The link to that is on the description of this video. I'm going to go down and I'm going to fire that up, and we're going to go out live on this channel on the Discord server. That'll be up and running in a couple of minutes, but there's probably some people over there right now, and I'll be available there to answer any questions that you all have. Okay, so let's just look at a couple of the comments that we have right here. Is the runway calculator specific for any aircraft? No, it's not. What you do is you go to your pilot operating handbook and you find the landing distance for your particular aircraft. You know, my aircraft, I think, is 1,200 feet landing, 900 feet taking off. I'd have to go back and look. It's been a little while since I've flown it. And I've flown a couple of other different aircraft in the meantime. But what you do is you take that number, and then that slide rule gives you a conversion that you need to make based on conditions. So it says you're going to have to multiply your landing distance by 1.5, for example. That's the way that works. So let's go see what else we have here. Yep, rate of change. That's with the carbon-14 dating. And, you know, whatever radioisotope you're using, you can generally get a pretty good estimate as to how old the object is. If you're somewhere approaching 1 half-life and you're less than about 10 half-lives. You know, if you have less than that, you're just missing, you know, a fraction of a percent of the original carbon-14, and your measurement error starts becoming significant. If you get out around 10 half-lives, you have so little of that carbon-14 left, it doesn't really, you know, the only thing that you would have after that would be contamination. One of the things that you'll see creationists talk about once in a while is finding carbon-14 in diamonds. There's no carbon-14 in diamonds. There's no reason for any carbon-14 to be in diamonds. Diamonds are well over 1 billion years old. If you find carbon-14 because you foolishly tried to test for it in a diamond, it's a contamination. It's just like the trick that they used with the rocks at Mount St. Helens that were supposedly 35 years old. They tested those using potassium argon, which has a half-life of 1.2 billion years. Do you think something like that would even remotely be able to give you an accurate estimate of 35 years? No, it won't. So what else we have here? Yes, Boomer U, indeed. Buzz Aldrin did use a 5-inch Pickett calculator on his lunar landing mission. All right. This went with all the Apollo programs. And that was simply the way engineers worked out in those days. They didn't have pocket calculators. You know, pocket calculators didn't come out until I think the Apollo-Soyuz mission had a pocket calculator with them, an HP, but I'm not sure. Let's see what else we got up here. Yeah, pocket calculators work just fine. On your iPhone, I don't know if you realize this, but if you pull up your calculator and you rotate the phone, it goes from a standard calculator to a scientific calculator. There are also secondary functions on that. So you hit the secondary button and your sine button becomes an arc sine button. And you can do all this on a calculator. The only problem that you run into with a calculator is you can get the wrong answer at light speed and have no idea why the answer is wrong. On a slide rule, you saw that there were very important things that you had to remember. There were certain operations that had to be done in specific orders. All right, you had to be able to estimate decimal places in your head. You needed to have a working understanding of logarithms. So what else we got in here? Yep, Colin, I'm kind of funny when it comes to this. When I was in middle school, one of the things that you couldn't do was use calculators on tests. If I was teaching middle school math, I would allow a student to use the slide rule. And the reason that I would allow a student to use the slide rule is that you have to understand the process in order to get the right answer on the slide rule. All right? You can't just mechanically punch stuff in. You have to actually know what you're doing. And if you do that, you've demonstrated what I'm trying to teach you in the 8th grade, and that's the principle. All right? I'm going to show you one other thing here real quick. I almost forgot to do this, and I'm glad I didn't. There we go. Now, you may recall that this thing right here is called an E6b Flight Computer. Now, a lot of people wonder about pilot watches. And if you look at the bezel on a pilot watch, it's movable. That's because the bezel is an E6b Flight Computer. I'm going to see if I can zoom in on this just a hair, because I'm going to show you how this works. Okay, so here's my wristwatch. Now, you'll notice that right underneath, there's a number of bezels under here. The inner one says 1 right here. That's 1 hour. And directly above it is a red 60 minutes. Now, my aircraft flies at 135 knots in 1 hour. So, what I do is I rotate 135 directly above the 60 mark right there. Okay, how far am I going to be in 2 hours and 30 minutes? So I go in to the 2 hour and 30 minute mark right here, and I read right up. It looks like it's going to be roughly 335 miles or so. You know, you read off the answer right out here. My fuel burn is 9.5 gallons per hour. My fuel tank holds 48 gallons, and I need to maintain 1 hour of fuel. So how far can I fly? A little over 4 hours. Okay. So if you need, for safety reasons, if you need to know exactly what your flight range is, that's fine. The bottom line is, in small planes, my bladder only lasts for 4 hours, so I'm going to be landing around here anyhow. It's not going to come into play. But I do need to know how much fuel I should land with, because my landing fuel adds weight to my aircraft, and my aircraft may have a landing weight. That's why sometimes you'll hear about airplanes having to burn off fuel in order to land. They're too heavy to land. Their landing gear will collapse. They can take off with that much weight, but they sure can't land with it. Now, I said that we were going to have an actual course on the E6b Flight Computer and things like that, so don't worry about not picking up everything. You can really do weird things with this E6b. On the back side, you can do wind triangles, which is kind of interesting because, you know, if you're flying north-northeast and you have a west wind at 15 knots, what's your ground speed actually going to be? So you can use that for flight planning. This thing will tell you, and it'll do it without electricity. So I guess that's about it for right now. I'm going to go get everything started on the Discord. I don't think that we have anything else that I have to address in the chat right now. I will be by on the live chat here in a couple minutes. Guys, today we were doing something a little different. I was making a raw video. Normally you wouldn't have seen the mistakes that I made, because I would have corrected them on the final video, and they will be corrected on this final video. But this is how a video is actually made. We've been doing this, what? Right around an hour, and I've got 3 more hours worth of work to do, and then this video will come out in the next few days on the Research Flat Moon production channel. And you all were a part of it. Thank you very much for sharing it with me, and I'll see you over on the Discord in a few.